Welcome to the deep dive. We take your source material and we really dig into the core insights.
Glad to be here.
So today we're tackling something pretty fascinating from the material you sent, trying to build, well, an intuition for quantum physics.
Yeah, and that's tough, right? Because it feels so counterintuitive. I mean, our brains, they're wired for the classical world.
Exactly. Solid things, predictable outcomes.
Uh-huh. And quantum mechanics as well, it's about this reality that's fundamentally, granular and fuzzy at the tiny scales.
Totally different from our everyday experience. So the mission, based on these sources, seems to be asking, can we use tools like visuals and analogies, maybe thought experiment,
Right.
to bridge that gap, to make the famously spooky stuff feel a bit less baffling? Can we actually learn to think quantum mechanically?
That's really the heart of it in these sources. They argue basically that you won't make quantum mechanics feel like dropping a ball,
No, probably not.
but you can sort of cultivate a new intuition by picturing the unseen, using these analogies and visual tools to build maybe alternative mental models.
Okay, so let's dive into that. How do these tools help picture abstract concepts? The sources mention circle notation for qubits.
Yeah, that's a neat one. So instead of just abstract symbols like tick and teletogate, you literally use a black circle for one state, a white one for the other.
Simple enough.
But the real power, I think, is showing superposition. That quantum thing of being in multiple states at once.
Mm-hmm.
You just draw a half black, half white circle. You instantly see the bothness, which is really hard to grasp just from equations.
That makes sense. It gives you a picture. And energy level diagrams, another visual mention.
Right. Those are key. They don't just say energy is quantized, they show it visually,
Mm-hmm.
like rungs on a ladder, discrete steps.
Okay.
And you can see particles literally jumping between these specific steps, usually by absorbing or emitting photons. It really hammers home that idea that they can't just hang out between energy levels in, say, an atom. Got it.
Yeah.
Okay, so applying these, what about classic quantum head-scratchers? Wave-particle duality. How do visuals help there?
Oh, the double slit experiment visual is just, well, essential. You picture sending particles, maybe electrons, one by one towards two slits.
Okay.
And what appears on the screen behind? An interference pattern, that wavy pattern. Classic wave behavior, even from single particles.
Which is weird in itself.
Totally. But then the visual changes if you add a detector. If you try to see which slit the particle went through,
Uh-huh.
the interference vanishes. You just get two bands like you'd expect from tiny bullets. Particle behavior.
Sure.
The visual contrast is stark seeing versus not seeing changes everything.
So the act of measuring forces it to choose.
In a sense, yeah. And for superposition, beyond the circle notation, there are analogies too, right? Like overlapping water waves, maybe?
Or the famous Schrodinger's cat thought experiment.
Right, the cat. Which, sounds grim, but it's a thought experiment. It's designed to show how absurd it feels if you scale superposition up to our world.
To highlight the measurement problem. Exactly. It pushes you to think about a system being in this fuzzy, probabilistic state until you look. It's not really about cats, it's about the weird implications.
Okay. And then entanglement. That spooky action at a distance.
The linked particles idea. The analogies help, like maybe two gloves separated, find a left one, you instantly know the other's right. Or correlated dancers.
Measure one, you know the state of the other no matter how far apart. Instantly.
Instantly, yes.
Yeah.
But, and the sources are really clear on this, it's crucial, you cannot use this to send messages faster than light.
Ah, right. That common misconception.
Yeah, because your measurement outcome on your particle, it's fundamentally random. You learn the state of the other particle, but you didn't control your outcome to send a 1 or a 0.
So you can't encode information that way.
Precisely. The correlation only shows up later when you compare your random results with the other person's random results using, a phone call or email. Normal communication.
Okay, that's a critical clarification. And back to quantized energy levels, the staircase or standing wave analogies help visualize why only certain energies are allowed.
Yeah, like a guitar string can only vibrate at specific frequencies to make a clear note. Same idea for energy in atoms. The diagrams show the allowed steps.
And this isn't just theory, right? This quantum stuff has real-world impact.
Oh, absolutely. That quantized energy idea, that's how lasers work, fundamentally.
Atoms jumping between very specific energy levels, releasing light.
Exactly, you engineer it. And these basic quantum concepts, they're the foundation for MRI machines using quantum spin.
Uh-huh.
And of course, the whole field of quantum computing, trying to harness superposition and entanglement directly for computation.
So understanding these basics opens up a lot. The sources also mention something about learning by doing, interactive tools.
Yes, that's a big point. Passive learning only gets you so far. Things like quantum flight trap were mentioned. These visual simulators where you can build quantum optics
So you
experiments.
can play around with it.
Exactly. You drag and drop components, send simulated photons, see entanglement happen, see measurement effects. It builds a different kind of intuition, more hands-on. You get a feel for the rules by seeing the consequences of your actions.
That sounds much more engaging. So wrapping this up then, what's the main takeaway? Building quantum intuition isn't about making it feel, I guess, normal or classical.
No, not at all. It's more about building a new mental toolkit, a vocabulary, visual aids, analogies that align with how quantum mechanics actually works, even if it's weird.
So visuals, analogies, interactive tools, they're like pathways into this really fundamental but strange layer of reality.
It's definitely a journey. Shifting your thinking from expecting classical certainty to embracing, well, the probabilistic and interconnected nature of things at the smallest level.
Okay, so here's a final thought to leave you with, something that really struck me. If measuring a quantum system is what forces it out of superposition, if the observer is needed to make reality, in a sense, definite, well, what does that really imply about the connection between us, the observers, and the reality we're observing? Is that link deeper than classical physics ever dreamed? Something to ponder as you continue exploring.